Welcome to Oddly Real. I'm Nem Stefanovic. I want to dedicate this episode to the speed of light. Interestingly, the value of the speed of light is actually defined to be 299,792,458 meters per second in the metric system. The precision of this constant speed has been tested in countless experiments. Oddly, it's not only a constant, but it's the same for any observer that's measuring the speed of light, whether that person is stationary or traveling at high speeds alongside it. It also happens to be the upper speed limit of the universe. But what would happen if we went faster than the speed of light? In fact, we can actually answer this question. Join us as we explore the very strange phenomenon of the speed of light. Let's start with an example where one observer is on a spaceship moving forward and they launch a model rocket in front of them while riding on the ship. There is an observer on the ground watching this. If the rocket is traveling at 4/5 the speed of light relative to the ground, and the model rocket is launched at 4/5 the speed of light, then we would expect the ground observer to see a speed of 4/5 plus 4/5, which is equal to 8/5, or 1.6 times the speed of light, right? In reality, what the ground observer sees is the model rocket traveling at 97% of the speed of light, which is still below the speed of light. So what happened? Our universe is not actually governed by 3 dimensions of space and 1 dimension of time as separate entities. Instead, it's one single unified 4-dimensional entity called spacetime. Spacetime has a special kind of geometry. It's Lorentzian. Specifically, space and time separations do not have the same values in different frames of reference for different observers. In our example, we have a person moving on a rocket ship while there is another person on the ground. Also, to make the explanations easier, we will talk about the passage of time not in units of seconds, but in units of meters. That sounds strange, but they are in fact actually totally equivalent units. It turns out that humans have been using the unit of seconds for convenience throughout history, yet meters and seconds are interchangeable. Seconds of time can be converted into meters of time by multiplying the seconds by the constant speed of light. For example, time in meters is equal to c, the constant speed of light, times time in seconds. So instead of saying 3.336 nanoseconds of time, we'll say the more convenient 1 meter of time. Keep in mind, we can say meters, seconds, years, or light years all interchangeably. Let's revisit the example above. Say the model rocket is launched from in front of the spaceship towards a target. The model rocket hits the target when it is 4 meters away as measured by the spaceship observer. The spaceship observer measures the flight time as 5 meters, so the model rocket speed was 4/5 of the speed of light. However, the ground observer doesn't measure the same distance or time between the two events. He is in a different reference frame. The distance the ground observer sees from the point where the model rocket is launched to the target is measured as 13.3 meters. The ground observer also sees the time separation differently as 13.7 meters. So ultimately, the speed of the model rocket relative to the ground is 13.3 divided by 13.7, which is equal to 0.97 of the speed of light. That's the behavior of the speed of light in a Lorentzian spacetime. No matter what observer is watching and no matter what speed objects are moving, the speed of light will never be exceeded for any situation. Yet, what if we could travel faster than the speed of light? For argument's sake, what would happen? Well, it turns out we have the theory and the knowledge to actually answer this question. So let's find out. Let's say it's the year 3000, and an inventor is working on a remote outpost in outer space. He's just created the blueprints for a faster-than-light engine. His excitement gets the best of him, and while he wasn't looking, his lab assistant takes the blueprints and some critical evidence of the work and escapes in his spaceship. The lab assistant wants the credit for the inventor's work, so he tries to reach the nearest human colony. The colonies are still a few light years away, and it'll take a few years to get there, but he has a head start, and more importantly, he has the proof of the work. The assistant rockets away at 60% of the speed of light. If the inventor left to pursue at the same speed, he'd never catch up. Also, sending a radio transmission to the colonies won't help in proving his case, and it risks others who are listening to steal the work for themselves. The inventor thinks about the problem and realizes that if he built the faster-than-light engine, he could catch up and take back the plans. He's already familiar with his own work, so he gets started. After 4 years, he has a fully functional faster-than-light spaceship that takes off in pursuit. The ship now travels at 3 times the speed of light, and it works. He passes space buoy markers 1 and 2 on his way, and he eventually catches up with the assistant's ship to take back his plans and the evidence. In order to understand this situation clearer, we can plot a spacetime diagram of the events that have happened from the reference frame of the lab on the outpost. We have arbitrarily chosen the reference time t equal to 0 to be the time that the faster-than-light ship leaves in pursuit of the lab assistant. Also, x equals to 0 is chosen to represent the location of the lab. This means that at time t equal to -4, 4 years earlier, is the point in time at which the plans and evidence were stolen from the lab, at x equals to 0. We trace the world line of the lab assistant from when they left the lab at t equal to -4 and at x equals to 0, as they travel further away in space, moving right, further along the x direction, and time moving up. Similarly, we follow the world line vertically up, tracing the flow of time forward for the inventor and the laboratory for 4 years while the new engine is being built. Notice that at time t equal to 0, 4 years later, the faster-than-light ship launches from the lab to eventually catch up to the lab assistant. See how the faster-than-light ship travels 3 units of space for every 1 unit of time, or 3 times the speed of light. But what does this look like from the perspective of the lab assistant? In order to find out, we can take the time and space coordinates of all the events as seen from the reference frame of the inventor's laboratory and transform the coordinates into those of the lab assistant's reference frame on the getaway spaceship. The transformation equations to do this are called the inverse Lorentz transformation. Remember that the lab assistant is on a spaceship moving at 0.6 the speed of light, so their observation of spacetime is different from the inventor's when in the laboratory. The resultant spacetime diagram is shown here. Let's start from the bottom of the diagram, the earliest part of the time, and trace the events as time flows forward from the lab assistant's reference frame in the spaceship. Notice that the spaceship has relative coordinates at x equal to 3, and it stays put at that point in space as we move forward in time. That makes sense, since this space-time diagram is from the perspective of the lab assistant on the spaceship, and they stay put there on the spaceship throughout their journey. Notice the lab seems to be moving to the left and getting further away in time. This also makes sense, since the rocket is moving away from the laboratory, but from the perspective of the rocket, it's the lab that's moving away. Notice that the laboratory world line traces up to a time t equal to 0, x equal to 0, which is the moment the faster-than-light ship heads off to intercept the lab assistant. However, if you look closely, something is very unusual. Notice that the lab assistant eventually encounters the faster-than-light rocket, event 3, but not as expected. It happens at time t equal to -1, which is 1 year before time t equal to 0 when the faster-than-light spaceship is built. Additionally, if we follow the world line of the faster-than-light ship, it seems to be moving backwards in reverse order of events. It is first at event 3, when it has intercepted the lab assistant ship, then it travels to marker 2, then marker 1, and ultimately arrives back to the laboratory. So what does this all mean? Well, cause and effect doesn't make any sense at all. There isn't a logical way to reconcile what's happening. This is all a result of assuming that an object can travel faster than the speed of light. There are also other issues when we start introducing velocities greater than the speed of light into our calculations. For example, a spaceship moving faster than light could emit 2 flashes of light from the same location on the ship, separated by some time. However, if we try to calculate the time separation from the ground observer's perspective, the result yields an imaginary value. This makes no sense, since values of time intervals are real numbers. Additionally, in the real world, particle accelerators have been accelerating electrons and protons to the greatest possible speeds with tremendous energy, and they have never exceeded the speed of light. Finally, it's worth noting that despite the limit on being able to travel faster than the speed of light, there is no theoretical limit to traveling as close to the speed of light as we wish. And that means that we can technically travel any distance in the universe for any desired interval of time for the traveler in their lifetime. So it's not all bad news. Thank you for watching this episode. I hope you learned something new. Remember, oddly real, really interesting.